Welcome to DAR Tutors for online and home tuition. Today, we will be covering key concepts from IB Chemistry Higher Level, focusing on chemical kinetics. Our main objective is to understand how we can describe and study the speed of chemical reactions. By the end of this session, you will be able to deduce the rate equation for a reaction from experimental data, determine the units of the rate constant, distinguish between unimolecular and bimolecular elementary steps, write rate equations for these steps, and determine the rate-determining step in a multi-step mechanism. Chemists use something called a rate equation, or rate expression, to summarize how changes in the concentration of reactants affect the speed of a chemical reaction. For a general reaction where A moles of reactant A react with B moles of reactant B to form products, the rate equation is written as rate equals the rate constant K times the concentration of A raised to the power of X times the concentration of B raised to the power of Y. Let's break down this equation. The terms in the square brackets, A and B, represent the concentrations of our reactants in moles per cubic decimeter, or mole dm3. The constant K is known as the rate constant. We'll discuss its properties in more detail later. Finally, X and Y are the powers to which the concentrations are raised. These are called the orders of the reaction. The power X is the order with respect to reactant A, and Y is the order with respect to reactant B. The sum of these individual orders, X plus Y, gives us the overall order of the reaction. It's extremely important to note that the orders X and Y are not necessarily the same as the stoichiometric coefficients A and B from the balanced chemical equation. The rate equation must always be determined experimentally. It cannot be predicted from the stoichiometry. Let's look at the different possible orders of reaction and what they mean for the rate. First, we have a zero-order reaction. In this case, the rate equation is rate equals K times the concentration of A to the power of 0. Since anything to the power of 0 is 1, the equation simplifies to rate equals K. This means the rate is independent of the concentration of the reactant. Doubling the concentration of A will have no effect on the rate. This is called a zero-order reaction. Next, there is a first-order reaction. The rate equation here is rate equals K times the concentration of A to the power of 1. This shows a direct relationship. The rate is directly proportional to the concentration. If you double the concentration of A, the rate will also double. This is a characteristic of a first-order reaction. Finally, let's consider a second-order reaction. The rate equation is rate equals K times the concentration of A squared. This means the rate is proportional to the square of the concentration. For example, if you triple the concentration of A, the rate of reaction will increase by a factor of 3 squared, which is 9. The rate increases 9-fold. This is what defines a second-order reaction. Now let's practice applying these concepts with a worked example. Consider the reaction. 2A plus B plus C gives 2D plus E. The experimentally determined rate equation is rate equals K times the concentration of A times the concentration of B squared. Our task is to determine the individual order of reaction with respect to each reactant, and then the overall order of the reaction. Take a moment to think about how you would solve this. Let's start with reactant A. In the rate equation, the concentration of A is raised to the power of 1. Therefore, the reaction is first order with respect to A. This means the rate is directly proportional to the concentration of A. Now for reactant B. The concentration of B is raised to the power of 2. This tells us the reaction is second order with respect to B. The rate is proportional to the square of the concentration of B. Next, let's look at reactant C. Notice that C does not appear in the rate equation at all. Any reactant that does not appear in the rate equation has an order of 0. So, the reaction is zero order with respect to C. This implies that changing the concentration of C has no effect on the reaction rate. Finally, we calculate the overall order of the reaction. We do this by summing the individual orders. The overall order is 1 plus 2 plus 0, which equals 3. So, this is a third-order reaction overall. Let's work through another problem. This time, we'll see what happens to the rate when two concentrations are changed simultaneously. The oxidation of bromide ions in acidic solution has the rate equation. Rate equals K times the concentration of bromate V ions times the concentration of bromide ions times the concentration of hydrogen ions. All reactants are first order. Let's say we half the concentration of bromate V ions and quadruple the concentration of hydrogen ions, while keeping bromide concentration constant. What is the effect on the overall rate? We can analyze each concentration change separately. First, for bromate V ions. The reaction is first order with respect to bromate V. Since we are halving its concentration, we expect the rate to also halve. Next, let's consider the change in hydrogen ion concentration. The reaction is also first order with respect to hydrogen ions. We are quadrupling its concentration, so the rate will increase by a factor of 4. Doubling the rate twice is the same as quadrupling it. To find the total effect on the rate, we multiply these changes together. The new rate will be the original rate multiplied by 1/2 for the bromate change, and multiplied by 4 for the hydrogen ion change. The product is 1/2 times 4, which equals 2. Therefore, the overall rate of reaction will be doubled. We've been using a value K in our rate equations. This is the rate constant. Let's explore what it is and its significance. The rate constant, K, is simply the constant of proportionality in a rate equation. It essentially tells us how fast a specific reaction is under a given set of conditions. Importantly, the rate constant is not truly a constant in the sense that it can change. Its value depends on factors like temperature, solvent, and pH. However, at a constant temperature, its value is fixed for a particular reaction and does not change as the reaction proceeds. One crucial point about the rate constant is that its units are not fixed. The units of K depend entirely on the overall order of the reaction. We can determine these units by rearranging the rate equation and substituting the standard units for rate and concentration. Let's take a general nth-order reaction with one reactant A. The rate is K times the concentration of A to the power of N. Rearranging for K, we get K equals rate divided by concentration of A to the power of N. The units of rate are mol dm3s1, and the units of concentration are mol dm3. Substituting these in, we get that the units of K are mol dm3s1 divided by mol dm3 to the power of N. Using exponent rules, this simplifies to mol to the power of 1 minus N, dm to the power of 3 times N minus 1, and S to the power of negative 1. We can use this general formula for any order of reaction. Let's apply the general formula for the units of K to the 3 common reaction orders. For a zero-order reaction, the overall order N is 0. Substituting N equals 0 into our formula, the units of K are mol to the power of 1, dm to the power of minus 3, and S to the power of minus 1. So, the units are mol dm3s1. Next, for a first-order reaction, N equals 1. Plugging this in, the units of K become mol to the power of 0, dm to the power of 0, and S to the power of minus 1. So the units are simply S1. Finally, for a second-order reaction, it's 2. Our formula gives us mol to the power of negative 1, dm to the power of 3, and S to the power of minus 1. The units are mol 1 dm3 S1. These are the 3 sets of units for K you will encounter most often. It's a good idea to commit them to memory, as they are a common test question. Let's work through a calculation problem where we need to find the rate constant. The rate equation for a reaction at 800 Kelvin is rate equals K times the concentration of A squared times the concentration of B. At 800 Kelvin, the initial rate was found to be 5.53 times 10 to the minus 4 mol dm3s1, when the concentration of A was 3 Hausdruck times 10 to the minus 2 mol dm3, and the concentration of B was 6 Hausdruck times 10 to the minus 2 mol dm3. Our objective is to calculate the rate constant K. To do this, we first need to rearrange the rate equation to solve for K. Rearranging the equation gives us K equals rate divided by the concentration of A squared times the concentration of B. Now, we can substitute the given experimental values into this rearranged equation. Substituting the values, we get k equals 5.50 times 10 to the minus 4, divided by the product of 300 times 10 to the minus 2, squared, and 600 times 10 to the minus 2. Let's simplify the denominator first. 3r times 10 to the minus 2, squared is 900 times 10 to the minus 4. So the denominator becomes 900 times 10 to the minus 4 times 600 times 10 to the minus 2, which gives us 540 times 10 to the minus 5. Dividing the numerator by this value gives us 10.2. Now, let's determine the units. We have mole dm3s1 on the top and mole 3 dm9 on the bottom. This simplifies to mole to the minus 2, dm to the 6, and s to the minus 1. The final answer is 10.2 mole 2 dm6s1. As a check, since the overall order is 3, 2 from A and 1 from B, and we found the units for a third-order reaction are mole 2 dm6s1, our units are correct. A key concept in kinetics, especially for first-order reactions, is half-life. The half-life, symbolized as T sub 1/2, is simply the time it takes for the concentration of a reactant to decrease to exactly half of its initial value. The beauty of half-life is that it provides a very straightforward way to determine if a reaction is first-order. Take a look at this graph of concentration versus time. For a first-order reaction, no matter what the initial concentration is, the time it takes for that concentration to halve is always the same. As you can see, the first half-life, from A to A2, is the same length as the second half-life, from A2 to A4. This property, that the half-life is constant and independent of concentration, is the defining characteristic of a first-order reaction. There is a very important mathematical relationship between the half-life and the rate constant for a first-order reaction. It is given by the equation T sub 1/2 equals the natural logarithm of 2 divided by the rate constant k. The natural logarithm of 2 is approximately 0.693. This equation allows us to calculate one value if we know the other. Let's do a quick example. If a first-order reaction has a half-life of 100 seconds, we can find the rate constant k by dividing 0.693 by 100 seconds, which gives 6.93 times 10 to the minus 3s1. The units are correct for a first-order reaction. We've seen that the half-life of a first-order reaction is constant. But what about for a second-order reaction? This is where the behavior is quite different. Take a look at this concentration versus time graph for a simple second-order reaction, where rate equals k times concentration of A squared. Let's track the concentration halving. The first half-life, the time it takes to go from an initial concentration of C to C over 2, is shown as T1. Now let's look at the second half-life. That's the time it takes to go from C over 2 to C over 4. Let's call that time T2. As you can see from the graph, the second half-life, T2, is longer than the first half-life, T1. For a second-order reaction, the half-life is not constant. It increases as the concentration of the reactant decreases. In fact, the half-life is inversely proportional to the initial concentration. This is a key difference that can be used to distinguish between first and second-order reactions graphically. We've learned to determine reaction orders from experimental data. But why do these orders appear in the rate equation? The answer lies in the concept of a reaction mechanism. A reaction mechanism is the complete sequence of tiny individual steps, called elementary steps, that a reaction takes to go from reactants to products. Most chemical reactions do not happen all at once, in a single step. We can describe elementary steps by the number of reactant particles involved. First, a unimolecular step. This involves only one particle decomposing or rearranging. The probability of this happening is quite high. Second, a bimolecular step. This involves two particles colliding and reacting. The probability of a successful collision is lower than for a unimolecular step, but is still common. Finally, a termolecular step involves the simultaneous collision of three particles. This is a very rare event and almost never happens in elementary steps. You're unlikely to see it in a mechanism. Now, the key connection. Since we know what particles collide in an elementary step, we can write its rate equation directly. For a unimolecular step, A reacting to give products, The rate is proportional to the concentration of A, so rate equals K times A to the power of 1. For a bimolecular step, A plus B giving products, the rate is proportional to the concentration of A times the concentration of B. So, rate equals K times A times B. The order of the elementary step is equal to its molecularity. So we can write rate equations for elementary steps. But what about for the overall reaction? For that, we need to introduce the concept of the rate-determining step. In any multi-step reaction, not all steps happen at the same speed. There is always one elementary step that is significantly slower than all the others. This slowest step is known as the rate-determining step, or RDS. Think of it like an assembly line. If one part of the line is much slower, it controls the speed of the entire factory. The same is true for a reaction mechanism. The rate-determining step is the bottleneck of the reaction. Its rate determines the rate of the overall reaction. Therefore, the rate equation for the overall reaction is determined by the reactants involved in the slowest step of the mechanism. Let's apply this principle to an example: the reaction between nitrogen dioxide and fluorine. The experimental rate equation for this reaction is rate equals K times NO2 times F2. Let's examine a proposed two-step mechanism. The mechanism proposes two steps. The first, between NO2 and F2, is slow. The second step, between an intermediate F radical and another NO2, is fast. According to the rule, the rate equation for the overall reaction should come from the slowest step. Step 1 is slow, so we write its rate equation. The molecularity is 2, involving NO2 and F2, so the rate is proportional to NO2 times F2. This mechanism correctly predicts the experimentally determined rate equation. This gives us confidence that this proposed mechanism is plausible. A key takeaway here is that intermediates, like the F radical, never appear in the final overall rate equation. Sometimes the rate-determining step is not the very first step. What happens then? We need a more sophisticated approach. Let's consider the oxidation of nitrogen monoxide with oxygen. The experimental rate equation for this is rate equals K times NO squared times O2. This is a third-order reaction. A single-step mechanism involving 3 molecules colliding is unlikely. Here's a more plausible two-step mechanism. Step 1 is a fast, reversible equilibrium between 2 NO molecules and an intermediate, N2O2. The second step is a slow, irreversible reaction between the intermediate N2O2 and an O2 molecule. Following our rule, the rate equation is determined by the slow step. This gives us rate equals K prime, times the concentration of the intermediate N2O2 and times the concentration of O2. But N2O2 is an intermediate. Intermediates are unstable and have very low concentrations, making them hard to measure. We need to express its concentration in terms of the reactants, NO and O2. To do this, we use the fact that the first step is a fast equilibrium. At equilibrium, the rate of the forward reaction equals the rate of the backward reaction. The rate of the forward reaction for step 1 is K1 times NO squared. The rate of the backward reaction is K minus 1 times N2O2. Setting these equal, K1 times NO squared equals K minus 1 times N2O2. We can rearrange this equation to solve for the concentration of the intermediate, N2O2. The concentration of N2O2 is equal to the ratio of the rate constants K1 over K minus 1, all multiplied by NO squared. Now we can substitute this expression for N2O2 into the rate equation for the slow step. This gives us rate equals K prime times the group K1 over K minus 1 times NO squared times O2. The terms K prime, K1, and K minus 1 are all constants, so their product is also a constant, which we can call K. Our final rate equation becomes rate equals K times NO squared times O2. This perfectly matches the experimental result. This mechanism is consistent with the evidence. Let's work through another worked example that uses a fast equilibrium to determine the overall rate law. The mechanism for a reaction is given by 2 elementary steps. The first step is a fast equilibrium where 2 molecules of M form M2. The second step is slow, involving M2 and a reactant K to form the product N. Our objective is to deduce the rate equation for this overall reaction. What is the overall order of the reaction? Remember the golden rule. The rate equation is determined by the slow step. Step 2 is the slow step, involving one molecule of M2 and one molecule of K. So the rate is proportional to M2 times K. However, M2 is an intermediate. We need to replace M2 using the fast equilibrium step. In the fast equilibrium of step 1, the rate of the forward reaction equals the rate of the backward reaction. So K1 times M squared equals K minus 1 times M2. Rearranging this for the concentration of our intermediate M2, we find that M2 equals the ratio K1 over K minus 1 times the concentration of M squared. Now we can substitute this back into our rate equation from the slow step. This gives rate equals K prime times the quantity, K1 times M squared times K. Just like before, we can combine all the constant terms into a new constant, K. The final rate equation is rate equals K times M squared times K. To find the overall order, we sum the exponents. The overall order is 2 plus 1, which equals 3. This is a third-order reaction. So far, we've focused on how rate equations are consistent with proposed mechanisms. Let's delve into another important tool: Arrhenius plots. The Arrhenius equation describes how the rate constant, and therefore the rate of a reaction, depends on temperature. The equation is K equals A times E to the power of negative activation energy over RT. Here K is the rate constant, T is the absolute temperature in Kelvin, and R is the gas constant, 8.31 J K1 mol 1, J, K1. E is the activation energy, in joules per mole, which is the minimum energy required for a reaction to occur. A is the Arrhenius constant, or pre-exponential factor, which accounts for the frequency of successful collisions with the correct orientation. This equation is useful but can be difficult to work with directly because of the exponential term. We can linearize it by taking the natural logarithm of both sides. The natural logarithm of K equals the natural logarithm of A minus the quantity activation energy divided by R, times the reciprocal of the absolute temperature. This equation is in the form of a straight line, equals mx plus c. If we plot the natural logarithm of the rate constant K on the y-axis against the reciprocal of the absolute temperature 1 over T on the x-axis, we will get a straight line. This is called an Arrhenius plot. The slope of this line will be negative activation energy divided by the gas constant, or EA over R. The y-intercept of the line will be the natural logarithm of the Arrhenius constant, A. This graphical method provides a powerful way to determine the activation energy of a reaction from experimental rate constant data measured at different temperatures. We've covered several key concepts. Now let's put our knowledge to the test with some IB-style practice questions. Let's start with a classic one: the iodine clock reaction. Question 1 states that the rate equation for the reaction of propanone with iodine in the presence of an acid catalyst is rate equals K times the concentration of propanone times the concentration of hydrogen ions. Using this information, we need to deduce the order of reaction with respect to propanone, with respect to hydrogen ions, and with respect to iodine. Let's work through the solution step by step. For propanone, look at the rate equation. The concentration of CH3COCH3 is raised to the power of 1. Therefore, the reaction is first order with respect to propanone. Similarly, for hydrogen ions, the concentration H+ is also raised to the power of 1. So the reaction is first order with respect to hydrogen ions. Finally, for iodine, I2. If you look closely at the given rate equation, you'll see that the concentration of iodine is not present at all. This means that changing the concentration of iodine will have no effect on the reaction rate. Therefore, the reaction is zero order with respect to iodine. This is a great example of why we cannot deduce the rate equation from the stoichiometry. The balanced chemical equation for the reaction includes I2, but it's not involved in the rate-determining step. Here is our second practice question, which tests your understanding of rate constant calculations. Question 2 asks you to calculate the initial rate of reaction given a rate equation, a rate constant, and reactant concentrations. To solve this, we just need to plug the given values into the rate equation. Our rate equation is rate equals 30.0 times 0.040 times 0.040. This gives us a value of 0.048. Now let's check the units. We have mol1 dm3s1 times mol dm3 times mol dm3. The mol1 term cancels with one of the mol terms. The dm3 term cancels with one of the dm3 terms. We are left with mol dm3s1, which are the correct units for a reaction rate. So our final answer is 0.048 mol dm3s1. Our next question is a multi-part problem involving the decomposition of hydrogen iodide. Question 3 states that hydrogen iodide decomposes according to the equation 2. Hi gas gives H2 gas plus I2 gas. The rate equation is rate equals K times the concentration of Hi squared. The reaction data is given for a temperature of 700 Kelvin. Our goal is to calculate the rate constant K and then determine the number of Hi molecules that decompose per second in a specific volume. Let's tackle part A first. We need to calculate kata. We rearrange the rate equation to K equals rate divided by concentration of Hi squared. Plugging in our values, K is 2.50 times 10 to the minus 4 divided by 2.0 squared. This gives us 6.25 times 10 to the minus 5. The overall order is 2, so the units of K should be mol1 dm3s1. We have mol dm3s1 on top and mol2 dm6 on the bottom, which simplifies to the correct units. So, K equals 6.25 times 10 to the minus 5 mol1 dm3s1. Now for part B. We need to find the number of molecules decomposing per second in 1 dm3. First, we must calculate the rate at the specified conditions. We use our rate equation with K and the Hi concentration. The rate is 2.50 times 10 to the minus 4 mol dm3s1. This means that in 1 dm3 volume, 2.50 times 10 to the minus 4 moles of Hi decompose each second. To find the number of molecules, we use the Avogadro constant. Number of molecules per second equals moles per second times Avogadro's number. That's 2.50 times 10 to the minus 4 times 6.02 times 10 to the 23. This calculation gives us approximately 1.51 times 10 to the 20 molecules per second. Our fourth practice question involves analyzing experimental data to deduce the rate law for a reaction. Question 4 presents a table of initial rates for the reaction between iodine, propanone, and hydrogen ions. Our goal is to use this data to determine the individual orders of reaction. The data table shows experiments with different initial concentrations and their corresponding initial rates. The strategy is to compare experiments where the concentration of only one reactant changes. Let's start by finding the order with respect to hydrogen ions. We can compare experiments 1 and 2 because the concentrations of propanone and iodine are constant, while the concentration of hydrogen ions doubles from 0.4 to 0.8. When the concentration of hydrogen ions doubles, the initial rate also doubles. This is the definition of a first-order reaction. So, the order with respect to hydrogen ions is 1. Next, let's find the order with respect to propanone. A direct comparison is a bit tricky, but let's compare experiments 2 and 3. Here H+ is constant, I2 is constant, and propanone increases from 6.0 to 8.0, a factor of 8.6 or 4.3. The rate increases from 3.6 times 10 to the minus 5 to 4.8 times 10 to the minus 5, which is also a factor of 4.3. Since the rate increases by the same factor as the concentration, the order with respect to propanone is 1. Finally, let's find the order with respect to iodine. We can compare experiments 3 and 4. Here the propanone concentration is constant, the hydrogen ion concentration is halved, and the iodine concentration is doubled. The rate goes from 4.8 times 10 to the minus 5 down to 2.4 times 10 to the minus 5, which is a factor of 1/2. Let's use the rate equation to figure this out. The halving of the rate, factor of atathathasas must be equal to the change in h plus c, factor of 1/2 times the change in I2, factor of 2 to the power of x. This means 1/2 equals 1/2 times 2 to the power of x. For this to be true, 2 to the power of x must be 1, which means x is 0. So the reaction is zero order with respect to iodine. Combining our findings, the rate equation is rate equals K times propanone times H plus. The overall order is 1 plus 1, which equals 2. Our final practice question is a classic Arrhenius plot problem. This demonstrates how we can find the activation energy from temperature-dependent rate data. Question 5 gives us a table of rate constant values for a reaction measured at 4 different temperatures. Our task is to plot the data, find the gradient, and calculate the activation energy. Here is our data table. Remember the Arrhenius plot plots natural log of K versus 1 over T in Kelvin. So our first step is to calculate these values for each data point. We must first convert the Celsius temperatures to Kelvin by adding 273.15. Then we calculate the reciprocal 1 over T for our x-axis. And finally, we calculate the natural log of K for our y-axis. Here are the calculated values. Note that 1 over T values are very small, so we use scientific notation. Now we plot ln K on the y-axis against 1T on the x-axis. Let's imagine we've done this. The data points should form a straight line with a negative gradient. To calculate the gradient, we pick 2 points that lie on our best fit line. Let's use the first and last calculated points for simplicity. The gradient is change in ln K over change in 1 over T. That's a 9.60 minus 11.99 divided by 0.003245 minus 0.003595. This gives us approximately 2.39 divided by 0.0035, which equals R6A229. The gradient is EA over R. We can use this to find the activation energy. We rearrange to find EA equals minus the gradient times the gas constant. That's 6829 times 8.31 JK1 mol 1. The negative signs cancel out, giving us 56769 J mol 1. Finally, let's convert this to kilojoules per mole by dividing by 1000. The activation energy is 56.8 kJ mol 1. Let's quickly recap what we've covered today. We started by defining the rate equation and understanding its components, including the experimentally determined reaction orders. We then distinguished between zero, first, and second-order reactions based on their rate equations and how their rates change with concentration. We also learned how to calculate and interpret the units of the rate constant, K, and the importance of a constant half-life for first-order reactions. Finally, we explored the fascinating world of reaction mechanisms, introducing elementary steps and the crucial concept of the rate-determining step, which allows us to predict the overall rate equation. Mastering these topics is essential for success in IB Chemistry HL Kinetics. If you're looking for more personalized help with IB, A-Level, or IGCSE curricula, please contact DAR Tutors for expert tuition. We are here to help you achieve your academic goals.